So, Mahadev had a really nice way of doing this. Okay, let me show you. So, we do not know how to do this. Okay, so let us first admit that we do not know how to do it directly. Okay. So, we break it into two steps. So, the first step is that I am going to convert my FHE encryption of S to some new special type of encryption, which sort of looping back to where we started actually uses these trapdoor claw free pairs. So, I am going to call it a TCF encryption. I will define it. Okay. So, obviously, we started with these trapdoor claw free function pairs. So, we want to use that somewhere and this is where it comes in. Okay. So, I am going to convert my FHE encryption into this TCF encryption, and then of course, I will use TCF encryption to do the above, to compute this encrypted C naught. Okay, these are my two steps. Are there any questions? So, what we will do is we will look at step 2 first and then we will look at step 1. Are there any questions? What have we done? We broke it down, our Toffoli gate, we broke it down to this funny little operation where you have encrypted FHE encrypted control bits and you want to end up with a quantum encrypted C naught, right. We broke it down to this. Now, we are saying that in order to achieve this piece, we will use these two steps. So, one is that this FHE encryption, I actually do not know how to use it directly. So, we will convert it to something that uses trapdoor claw free function pairs, okay. And we will use these trapdoor claw free function pair encryption, which I will define to achieve this encrypted C naught that I want. Is it clear? Okay, so let me show you what is this TCF encryption. So, what do I want to do? I want to I want to encrypt a bit. Okay. So, I define the TCF encryption of a bit S as a TCF function pair f0 f1 that goes from some x to y. Here what I will do is that I am going to break x as 0 1 times r. So, I am sort of splitting the domain into a single bit times the rest of the space. Okay. This is, I mean, we can do that. So, we are given a function, we just sort of, it is just a conceptual thing. So, I split it in this way. Okay. So, now I have this function pair and I want to use this function pair to somehow encrypt a bit S. So, how do I embed the bit S into this? Okay. So, I embed it as follows. I define I require that for all clause mu 0 r 0 mu 1 r 1. I hope that this notation is not confusing anybody. So, this is our erstwhile x 0 and r x 1, right. So, for all clause mu 0 r 0 mu 1 x 1, it holds that mu 0 XOR mu 1 is equal to S. So, this is my TCF encryption. So, basically the way that I am encoding a bit is that I am taking a function pair and I am somehow setting it up so that for any claw that exists, right, the first bit of the pair XORs to the secret bit S. Now, you may feel that this is an unnatural definition. Well, at this point we will just say that I can define it. Of course, later we will also have to construct it, we will do that. We will do that using an FHE encryption scheme. Okay. But certainly we can define it, right. So, is the definition clear to everybody? So, it is basically this TCF pair which we have already defined, and how does it encode the bit S? Well, for every claw the first bit of the pair XORs to the secret bit S. This is my definition, alright. And it turns out actually that if I have such a TCF encryption, then this step 2 of computing an encrypted C0, this surprisingly becomes easy. So, the main novelty is in figuring out this connection. Okay. Once you have this kind of an encryption, this encrypted C0 computation that I wanted, this actually becomes easy. And how do you think we will do it? So, unsurprisingly, because of the way we have set it up, unsurprisingly, we are going to use a superposition over the claw. Okay. So, we will compute the following. Okay. So, okay, now use TCF encryption to perform the encrypted C0, right. This is what we want to talk about next. And how are we doing it? Well, I have something like this, right. So, I have some psi which is AB, alpha AB, right. This is my C0 input, okay, right. So, I have this pair AB as my input, okay, and I have an encryption of a bit S, remember. So, there is a control bit S and I have now a TCF encryption of that. And what do I want? Can anyone remind us what we want here? Given this input state psi and an encryption of the bit S, what is it that I want? I want a quantum encryption of AB, alpha AB, A, B XOR AS, isn't it? This is what I want. I have this and of course, I have enc S, right. S is an input to the operation, it has to be there somewhere. So, I mean I have a quantum state and I have a classical encryption and I want to end up with this following thing. Okay. So, here is what we do. Okay. So, now given F0, F1, I am going to sample a random y in the image and entangle psi with the corresponding claw. Now, we already saw how to get a superposition over the claw, and now what we are doing in addition is that we are going to sort of entangle it with this state psi that we started with. Okay, and this is not hard to do. So, just for completeness, let me just write it down. So, I want to go from psi to the following. So, to some b alpha 0 b 0 b x 0 plus alpha 1 b 1 b x 1, where x0 x1 is a claw. Okay. So, this is obviously not what I want. So, it is not the final outcome, but it is the first step. Okay. So, let us make life simpler for ourselves and kind of get rid of the B just for simplicity, for ease of exposition. Should we go over how we do this entanglement? Maybe this is not hard to see, so it is worth doing. So, this is done as before. Okay, so summation over x, I prepare this state, okay, summation over x psi x 0. Okay, so what is psi over here? So, psi is summation over a b, right, alpha a b a b. So, this is this, just expand it out. Okay, and I can transform this to summation over a b x, alpha a b x f a x. Okay, let us stick with the notation here. So, I can apply the unitary from before, and now I can measure the last register, and this will give me summation over b alpha 0 b, 0 b x 0 plus alpha 1 b x 1. Okay. Any questions? So, this is how we are going to construct our superposition over the claw, entangled with our our state, right. So, this is our state, right. Now, as I was saying before, for simplicity, let us get rid of this b. So, for simplicity, I am just going to set b equal to 0. Everything that we do from now on can obviously be extended to incorporate this b. This is just for ease of exposition, okay. And recall that b is one of the C naught inputs. So, I am just sort of taking it out of the picture. So, now if I remove the b, then what did I get? I got summation over a 0 1, a is binary, okay, alpha a x a. So, this is a nice clean expression that I can stare at, right. So, it is just what we have above highlighted in the yellow, but I just removed the b from it. Everyone convinced that this is just what we had, and I am just simplifying it. Okay, great. Now, since I have so what is my x a? I have some structure here, right. So, what is this? This is alpha a and this is mu a r a, right. So, remember that x a, any x, the domain we split it into a bit times something else, right. So, I am just rewriting x in terms of these components, okay. And now this is where things start looking like what we were hoping for. So, I claim that mu a can be written as mu 0 XOR a s. I claim this. Can anyone see why? So, I am writing mu a as mu 0 XOR AS. Do you see that this works? So, if A is 0, then mu 0 XOR AS is just mu 0. Okay. If A is 1, then mu 0 XOR AS is mu 0 XOR S, and mu 0 XOR X is mu 1, because mu 0 XOR mu 1 is S as we defined in our TCF encryption. So, very nice. I mean, you know, this is starting to look like what we wanted, right. So, in fact, remember what is it that we wanted. So, we wanted like a summation alpha A S, right. Remember, it was B XOR AS, but now we have removed the B. Okay. So, what is it that we wanted? We wanted something like this, right. So, we wanted a summation over A alpha A you know AS. We wanted something like that. Of course, you know, we wanted this to be encrypted using QOTP. Okay. But this is essentially the state we wanted. Now, what we have is really close, right. So, what is extra? So, you know, this mu 0 looks extra, R 0 and R 1 look extra, right. So, it turns out actually that you can you can actually transform these to get a QOTP of the state that you want. So, what we got, okay, let's you know, let's go slowly. So, what did we get? We have this, right. We have a summation alpha A mu 0 XOR AS R A. Okay. What is it that we want? We want like a QOTP of this, right, of summation alpha AS. We want a QOTP of that. So, we want some, you know, x to the little x, z to the little z of this guy, this summation A alpha AS, right. So, are there any questions? You need not have understood how we got this thing that we wanted. I am just trying to point out that we have made progress, we have come close. So, you know, did everybody understand how this thing worked out, this thing where I have the question mark, everybody understood that. So, now all that I am saying is that, you know, this is pretty close to what we wanted, that is all I am saying, and what we wanted is in this pink at the bottom of the page, right. This is what we wanted. So, what is the difference between what we have and what we wanted? Well, one thing is that this mu 0, R 0 and R 1 look extra. This is extra, and there is also something which is missing. What is missing? The OTP part, right, the x to the something, z to the something times the state that we want, right. And what I am telling you now is that actually this mu 0, R 0 and R 1 are what will give you the OTP that you want. They will give you the x to the something, z to the something, okay. And I will not show this in full detail, but you know, we'll try to understand it. So, let's okay. So, extra is mu 0 R 1 and mu 0 R 0 and R 1, and missing is the OTP padding, right. So, the x to the x and the z to the z, and my claim is that this actually can be converted to this is my claim. The extra stuff can be made to give us the missing stuff, this is the claim, okay, and we will see why this is true. So, does everyone at least see what we are trying to do over here? Okay. So, I am going to rewrite my A alpha A mu 0 XOR AS R A. Okay, I am going to write this as I tensor x to the mu 0 tensor I summation over A alpha A S R A. Okay, this is just a rewriting. And what we are trying to highlight here is that this mu 0 XOR AS, right. Mu 0 XOR AS means what? It's a bit flip. If mu 0 is 1, then it flips this AS, right. And isn't that exactly what the X gate does, right? The X gate is a bit flipping gate, right. So, intuitively what is happening is that this mu 0 is acting like a classical one time pad to hide the S which I need to hide, okay. But the classical one time pad is not enough, I need a quantum one time pad. So, I also need Z's to start coming in and the R's will be used for that. So, the mu 0 is giving me the X and the R's, I am going to show you how to use those to get the Z's. So, does everybody follow the connection at least between this top state and the bottom state? So, I am just rewriting it in terms of an X operator and now I am making this form of the state look even closer to what I wanted, right. So, this mu 0 XOR thing I removed it and made it an X operator which I wanted. Now, I have these R's hanging around and I want to also remove them from the state and instead get some Z operators, right. So, it turns out that you can get that by performing a Hadamard and taking a measurement. Okay. So, these are our we will see. So, good. So, turns out that if we perform a Hadamard and measure the register containing RA, okay, and when we measure, let us say that we get some output D, then the resultant state looks like this. It looks like this, Z to the D R0 XOR R1 tensor x to the mu 0 summation over A alpha A AS, which is exactly what I wanted. So, I am not going to do the calculation in class where we apply the Hadamard and perform the measurement. Okay. So, you can try it out at home. So, what should happen is clear, right. So, I have this state over here, right. I am going to apply a Hadamard to the RA register and then I am going to perform a measurement. So, it's just some careful algebra, okay. You can work it out. So, you will get some -1 to the RA times gamma whatever, right. You can work it out. So, you will get what? You will get this. So, now we look in really good shape, isn't it, because this is exactly what we wanted. This is a QOTP of the state that we wanted, okay. And we had ignored one B register, everything will work out if you also have the B, okay. So, we are just you can check that. So, this is great. So, what is it showing us? What we saw is that if we have a TCF encryption of the bit S, we do not have that in fact, right. We have an FHE encryption of the bit S, but suppose we had a TCF encryption of the bit S, then doing this doing this process, which is entangling the state with the claw, okay, gives us something with some extra mu's and r's, which with a little bit of manipulation can become a QOTP of the state that we wanted. Okay. This is exactly the encrypted C0 state that we wanted, right. So, this is our desired output. So, what is our missing piece now? The TCF encryption, right. So, I do not of course have the TCF encryption. So, let me go back to the two steps that we said, right, we wanted to do. So, we said we will do these two steps. For this encrypted C0, we will convert FHE encryption to the TCF encryption, and then we will use the TCF encryption to compute the encrypted C0. So, we have done step 2. So, now we need to do step 1. Okay. Are there any questions about step 2?